Hi students, welcome to my lectures on chemical engineering thermodynamics. Today we are going to compare the fugacity of the pure gases as well as the fugacity of the gases in a gas mixture. So we are going to analyze these two using a model which is called ideal gas mixture model. The model itself suggests that if two or three gases are there in a mixture which are behaving ideally, okay, then how we have to deal with that kind of gas mixture. And in addition to ideal gas mixture model, and I am going to parallelly put one more model which applicable for non-ideal gases. So on the left hand side you are going to see if every gas is behaving ideally, how the equations and formulas look like. On the right hand side, okay, on right hand side of the board you can see that how the same gases in a mixture is behaving non-ideally, then how we have to formula is going to change. And later on I am going to show you with a small example, so it will be more clear. Okay, let us come to the board. The today's concept is fugacity and fugacity coefficient. Actually this is coefficient of species or gases in the gas mixture. In other words, I mean the other parallel concept is, now today we are going to learn about what is ideal gas mixture model. Okay, as you have learned about how to analyze the Gibbs energy of the pure components, Gibbs energy of the components in a mixture, we are going to use those formulas to compare the ideal gas mixture model and the non-ideal gas mixture model. Let us see. On this side I have shown what if every gas is behaving ideally, whether pure gas or mixture of gases. On this side, how a non-ideal gas behave when it is pure state, and second when it is in mixed state. Okay, let us see. If you remember, you imagine this is the pure gas, only the molecules of A are present which are at a certain temperature and pressure. The Gibbs energy of this pure gas in this container is GaIg. Ig is representing the ideal gas. On the right hand side it is the same pure gas which is behaving non-ideally at same temperature and pressure conditions, and Ga is representing the Gibbs energy of this particular A in a non-ideal gas. So the here it is Ig is there, that means ideal gas. Here the Ig has been removed. This is how we have to take non-ideal gas notations or representations. And here the similar way, it's a mixture of gases A plus B. What happens if it is an ideal gas mixture, and on this side what happens if it is a non-ideal gas mixture? Suppose A and B are present, which are A fraction is Ya in this mixture, B fraction is Yb in the mixture. T and P is the temperature and total pressure in this container. In this container total pressure is P, then the partial pressure of A is Pa and the partial pressure of B is Pb. And what is the partial molar Gibbs energy of A is nothing but G bar A Ig. What is the partial molar Gibbs energy of B is nothing but G bar B Ig. Because it's an ideal gases, mixture is also behaves ideally, so Ig will be there. Ig is representing the ideal gas mixture. On the right side you can see same container, A and B is there. Now Ig has, everything remains the same, temperature and pressure, everything remains the same. The only thing is now Ig is removed everywhere. Here G bar A Ig, it is Ga bar. It is G bar B Ig, this is Gb bar. Because it's a non-ideal gas, ideal gas state has been relaxed. In addition to that, I have represented with partial pressure Pa, this is partial Pb. On the side of the partial pressure A, I have represented one more notation which is called fugacity of A in the mixture, which is represented by Fa cap. Okay, that means if A molecules in this mixture is behaving non-ideally, the non-ideality of this A is represented by Fa cap. And non-ideality of B is represented with the term FB cap. The caps representing the non-ideality in the mixture state. And here I have, if you look into the pure gas, I mean non-ideal, if a pure gas is behaving non-ideally, the non-ideality of this pure gas is represented by Fa. Fa means pure gas fugacity of A. P is the total pressure. F is the fugacity of A in the mixture. Okay. Now you have understood the comparative statements. Okay. Here only the thing is, there is no fugacity term here. Here additional fugacity term has come along with the partial pressures. Okay. Now you can look into this equations by picturizing this. Okay. For the pure gas, what is the Gibbs energy of A? Integration constant plus RT ln P. P is representing the total gas, I mean pressure in the mixture. The alternative expression for the non-ideal gas is Gibbs energy of I. That means any gas is represented by integration constant plus RT ln F. F is representing the non-ideality of the pure component in the container. Here it is total pressure P, it is fugacity F. There is a comparative statements between the ideal and non-ideal states. Okay, similarly, when you talk about the mixture, the partial molar Gibbs energy of any component is represented by G bar I Ig. When the G bar I Ig is nothing but the chemical potential of A in this mixture. So, chemical potential of any component in this mixture is integration constant plus RT ln Pi. What is this Pi? Pi is representing the partial pressure of that particular component in the mixture. Okay, and same statement can be rewritten and replaced with the partial pressure with Yi into P. As you know, partial pressure is nothing but mole fraction into total pressure. So simply I replace the Pi with Yi into P. So these equations are for the ideal. The top one is for the pure state and bottom two are for the mixed state. Similarly for the non-ideal mixtures. See, Gibbs energy of A in this mixture is nothing but integration constant into RT ln F, F representing the fugacity. For the mixture state, okay, the partial molar Gibbs energy of I is nothing but the chemical potential of I in non-ideal state. That means I am talking about this is integration constant plus RT ln Fi cap. Okay, here it is the partial pressure, it is the partial, you can talk in terms of a partial fugacity. Okay, fugacity cap. Okay, the partial pressure is replaced with the Fi cap. Fi cap is representing the partial fugacity of I in this mixture. Okay, this is how. And Fi, so let us keep the Fi as it is. Okay, for the more comparative statements, and let us see what the other statements are. Okay, I can replace Fi with, similar it is Yip. If I replace Fi till ln phi I Yip. Okay, it will come like that. Don't worry how this came, I will let you know. So okay, now you have keep this thing in mind. Let us observe this now. Okay, if you know the fugacity of pure coefficient of pure component is nothing but fugacity by pressure. F by P is nothing but fugacity coefficient of A in this mixture. So if it is A, only pure gas, the fugacity coefficient of A is nothing but fugacity of A divided by total pressure. Similarly, if I talk about the mixture is also having some fugacity coefficients because there are two components present in this mixture. There will be two fugacity coefficients, one to the fugacity coefficient of A, second is for the fugacity coefficient of B. Okay, then any component, the fugacity coefficient in this mixture is represented by phi I cap, is nothing but Fi cap by Pi. Fi is the partial fugacity of I in this mixture divided by Pi means partial pressure of that particular component in the mixture. For the case of A and B, fugacity coefficient of A cap, that means in the mixture, is nothing but partial fugacity of A divided by partial pressure of A. Similarly, fugacity coefficient of B in the mixture is nothing but fugacity coefficient of B divided by partial pressure of B. As you know, partial pressure of A is nothing but Ya into P, partial pressure of B is nothing but Yb into P. Okay, this is how the fugacities and fugacity coefficients are related. For ideal gases, if this mixture is behaving ideally, then what will be the main reason? The fugacity coefficient is equal to 1. That means Fi by P equal to 1. That means F equal to P. That means for mixtures, those are close to ideal, then fugacity will be equal to pressure. Okay. Similarly, for the case of A, phi A equal to 1, that is nothing but Fa by P equal to 1, that is nothing but Fa equal to P. For the case of non-ideal gas mixtures, fugacity coefficient of I in this mixture will be equal to 1. That is fugacity coefficient of I equal to 1, that means Fi cap by Pi equal to 1, that is nothing but fugacity coefficient of I is equal to partial pressure here. For the case of A and B, fugacity coefficient of A in this mixture equal to 1. If it is behaving ideally, the fugacity coefficient of A equal to 1. That means Fa by Pa equal to 1. That means Fa equal to Pa. Pa is nothing but Ya into P. Okay. Similarly, it is for the B. So now you can observe the comparative statements. Okay. One is for the one behaving in an ideal gas way and one is behaving non-ideal gas way. So you can compare the ideal gases and non-ideal gases with the term the fugacity coefficients and fugacities. So let us apply these formulas in this example so that it will be more clear. Suppose in example 1, there is a pure component of A gas is present at temperature 100 and pressure 3 bar. Fugacity coefficient of A is already given, is a 0.5. In the last class, I told you that fugacity coefficients can be estimated using number of methods. One is through experimental data, second is through equations of state, third is through generalized correlations. Okay. If the fugacity coefficient is given, what is the fugacity of A in this mixture? Is nothing but phi A into P. That is 1.5 bar. Now you see, the pressure, even though the pressure is 3 bar here, the actual driving force for reaction or separation to happen is only 1.5 bar, not 3 bar. Okay, because the fugacity coefficient is 0.5, the driving force has been reduced to 1.5. Similarly, the example 2, what is the fugacity, partial fugacity of A and partial fugacity of B in this mixture you have to estimate. Given at temperature is equal to 100 and pressure equal to 3 bar, and fraction of Ya is given 0.5, fraction of B is given 0.5. Then fugacity coefficient of A in this mixture is 0.9, fugacity coefficient of B in this mixture is 0.8. Now you have to find out what is the fugacity, partial fugacity of A in the mixture. That means Fa cap. Fa cap can be calculated using fugacity coefficient of A in this mixture into partial pressure of A. The partial pressure of A is nothing but the fraction of A into total pressure. Total pressure is given, fraction of A is given. So 1.35 bar. Similarly, partial fugacity of B in this mixture is 1.2 bar in the similar way. Okay. Now you can compare. When the partial pressure is of A is 1.5, what is the fugacity of A? Fa cap, okay, Fb cap, only 1.35. When the partial pressure of B in this mixture is 1.5, what is the partial fugacity of B? Is 1.2. Even though, so if you go with the ideal way, you are designing a separator or a mixer or a reactor based on 1.5, you will be underestimating. Why? Because the real driving force is 1.35, but you have used 1.5. So in reality, you won't achieve the target. So always you have to design the things based on the real driving force, not on ideal driving force. Similarly for B, the driving force for anything to happen is 1.5 bar, and reality how much is 1.2. That means you can see here also you are trying to underestimate things. So always you have to design the things based on real driving force. That means you have to take care of the non-ideality of the gases. Okay, I hope now you can able to easily understood and remember okay, what is happening in the ideal gas mixture, non-ideal gas mixtures, and how to deal with the things with the non-ideality, then what is the implications of non-ideality in the through this example. and let us meet with the new lecture. Thank you.